Hello everyone, welcome back to AI with Manvinder. So by now, if you have been into data science and machine learning field, you know how decision tree works. The math, the splits, the criteria. But I want to be honest about something. Even after understanding all of that, I still had this uncomfortable feeling. Like I knew the concepts, but I didn't fully own them. Take depth for example. I know increasing the depth makes the tree more complex and eventually leads to overfitting. I can say that confidently. But when I was actually tuning a model and looking at results, I wasn't actually sure why it was behaving in a certain way. I was guessing. And that's the gap. If I can see what each hyperparameter does visually in real time, I don't need to guess anymore. I can look at a decision tree boundary and immediately know what's happening and what to fix. That's the real confidence. So that's exactly what this playlist is about. Change a hyperparameter, see what happens instantly live. No slides, no theory, just a live dashboard viewer. I move one slider and the decision boundary updates in real time. And I am starting with decision trees because they are the most visual algorithm we have. Every split, every branch, every leaf, you can see the logic, which makes them perfect place to build this kind of visual intuition. And honestly, once you have this for decision trees, you every ensemble method built on top of it, be it random forest, XGBoost, gradient boosting, start making more sense too. So let's get into it. Here, today's dataset, a telecom industry, one goal to predict whether a customer will churn from a telecom subscription or not. And the data available is contract type, month to month or annual, monthly charges, what are they paying, support tickets, how many times did they call support in last 6 months. Now, even before running the model, I can reason about it. Month to month customers, switching cost, and they can leave tomorrow, no penalty. Churn risk is already very high. Contract, and if the customer having annual contract, they have committed and risk is lower. So let's see if the tree agrees. So I train the model and look at the root node, the very first split, contract type. So algorithm found the exact same signal a senior telecom analyst would find. That's not luck. That's a well-trained decision tree doing its job. For month-to-month customers, the next question is monthly charges. High bill, no commitment, right? So that's your high churn risk. The person is paying a lot and has every reason to look elsewhere. For annual customers, the tree looks at support tickets. Locked in but frustrated, right? Three or more tickets in 6 months means they are not happy. They are not happy with your services. So they, at the moment the contract ends, they will leave. Quick terminologies. Root node. This is the first question, the first split, that's the most important feature. Internal node, these are intermediate decisions or questions any decision tree has made. Leaf nodes are basically the final prediction, no more splits after that. Branch is the yes no connection between the nodes. Depth, how many levels from root to leaf. Essentially, how many questions the model is allowed to ask. Got it? Now, good. So decision tree comes into two flavors. Like it is adaptable for classification as well as regression problems. Like predicting a category in classification, in the regression it is predicting a number. Um, in the classification, the split quality is defined from Gini or entropy, while in regression it is MSE or ME minimization. Same tree, same logic, different measuring stick. That's the only difference. So what are the hyperparameters, right? So hyperparameters are like max depth, minimum samples leaf, and so on. But how does this impact my overall decision boundary? For that, I have built a live dashboard, real data set, real decision boundary, live visualization. We are going to change depth, minimum samples, criterion once at a time and watch the boundary shift in real time. All right, so here's the dashboard. We have a few different data sets to play with, and I can choose any one of them. Some are easy to separate, some are complex. I'm starting with the simplest one. I'm taking 500 samples with low noise level. and the classes are easily separable in a circular manner. So red and green are the two classes. And now I'll start tuning the hyperparameters and see how decision boundary is changing in real time. First up, max depth. So this controls how deep the tree is allowed to grow. At depth is equal to 1, the tree is allowed to only one split. See, just a single one split. It is cutting through the data and very simple, very biased. Now if I increase it to say 4, the tree has grown to depth 4, 1, 2, 3, and the fourth is the final one. And the boundary, now I can easily separate. My training accuracy and test accuracy has improved. I'm able to split it better, right? If I keep it increasing like 4 to say 10, what happens? So now this is more able to split my data sets in a very better way. So next step is basically the primary control for tree complexity. In practice, you rarely want to go above 7 or 8 unless your data is very complex. If I reduce it and go to the second one, that is minimum sample split. This is the constraint at the internal nodes. Right now it is set to 2. So basically the intermediary node will split further if it has 2 samples with it. If less than that, it will not split further. If I increase it, so basically intermediary node will require more data, more samples for the further split. That is again another way of using the overfitting. So basically if it is low, then I am aggressively pushing for the splitting. But if it is high, I'm discarding the aggressive splitting. For example, if I make it to say 12, this is how. So every intermediary node will split only if they have more than 12 samples. Next one is minimum samples leaf. So is basically after the intermediate node splits, how many samples one leaf can have. Right now it has 1. Basically says leaf node must contain at least these many training samples. So it is 1 that I'm aggressively pushing for further splitting. Basically I'm allowing the splitting at the decision node. If I increase it, so what that means is now, so if I increase to 6, the tree won't create a leaf unless at least 6 samples support that prediction. The decision boundary becomes smoother, the predictions are more confident because they are backed by more data, and aggressive splitting is discarded. So next feature is max features. This control how many features the tree consider at each split. Right now it is set to square root. I can change it to log, or if it is set none, then it consider all features at every split, maximum power, but high risk of overfitting. In practice, square root or log 2 are the good for default for prediction or for classification. They balance accuracy and generalization. Next criterion, whether I'm going with log loss, Gini or entropy. So next is splitter, is either random or best. Best tree is basically where the tree evaluates all possible threshold and finds the absolute best one. This gives you the optimal split, but it is slower if the data set is very large. Random is where what we have now, tree randomly samples thresholds and pick the best among these, faster and more generalized. Next is max leaf nodes. This is another way to control complexity. Instead of limiting depth, we are limiting the number of leaf. Right now it is set to 2. So basically, and I can increase to have force for say 9. I'm forcing it and I'm forcing it to have 9 leaf nodes. 1, 2, 3, 4, 5, 6, 7, 8 and 9. It is actually very elegant hyperparameter because it directly ties to your business logic. So suppose you want to have exactly 5 customer segments. So you can set max leaf nodes to 5. The final is the minimum impurity decrease. This is a pruning mechanism. It says only make a split if it decreases impurity by at least this much. Currently this is 0. So every split is allowed, and no matter how small the improvement is. If I increase the split to say 0.1, so none of my split is currently giving me better decrease, so splitting is discarded. So if I reduce it, it will allow me to have more splits. So this is all hyperparameters, and this is the feature importance. I can fetch it out of it, and overall visualization of hyperparameter gives us the best understanding of how it is affecting the overall decision boundary to understand the algorithms much better. This is all for this video. In the next videos, we will continue our playlist, and we will deep dive another machine learning algorithms like support vector machine, random forest, or XGBoost, and we will play with their hyperparameters. And don't forget to like, share, and subscribe. This is Manvinder Chahar, and you are at the channel AI with Manvinder. Thank you so much.